Welcome to TryRide. In Module 2, we are discussing about backtracking in artificial intelligence, Part B. Backtracking search. Backtracking search is a depth-first search algorithm that incrementally build candidates for the solutions. Abounding a candidate backtracking as soon as it determines that the candidate cannot possibly be a completed to the valid solutions. So usually backtracking is a search, right? So when it combines the backtracking search is a fundamental algorithm technique in a artificial intelligence used for solving various problems, especially those that involve the finding all or some solutions to problems like static size and specific contents. Okay, in mostly it use it in construct. It often is applied to the construct satisfaction problem, CSPs, planning problem, and games like that. Uh, we can you can take a concept like we can imagine you're trying to solve a maze and you move forward making choice at the one edge of one junction. If you hit a dead end, you won't just give up, right? So you backtrack to the last junction where you start from the junction and where you had left over the route, and you choose that sudden route to reach the dead end. So you backtrack yourself and go back to that part, and you choose an like we choose the unexplored path and try to different direction. Like with the help of the backtrack we use. So what is constant satisfaction, right? So we also know in previous lecture we discussed about the construct satisfaction. CSP is a problem characterized by three types, right? What are the variables, domain, and constants, right? So a set of variables. We can also know that a set of elements that need to be assigned values that typically denoted by as x1, x2, and x of n, right? So up to x of n. So infinite, like so in Sudoku puzzle, each empty cell on the grid it will be variable like that. We take an example in previous. So in domain of each variable xi has domain di of the possible values, right? So for each variable xi, and there is a domain di, which is a set of all possible values that xi can take, right? So constant, a set of constant that specify allowable combination of values for subset of variables, right? So a set of rules or conditions that specify allowable combinations of for subject, like we can set the subset of the variables, those constant limit to the possible assignment to the variable. The goal of the CSP is to find an assignment of the value of to all the variables, right? So for the respective domains, such that all the given constant are the satisfied. So here we have steps involving backtracking. So we have few steps here. Initialization, start with an empty assignment. So there is a starting point. There is a starting point of the search, right? You begin with no variables assigned a value. And the goal is to be built a complete assignment where every variable has a value and constant or satisfied. Selection, choose an unassigned variable. Choose an unassigned variable like at the each step of backtracking process. You need to decide which variable to try and assign it a value to text, right? So there are various stages. Heuristic for the doing this such as like most concentrated variable, and we have a degree heuristic variable like that. So assignment. So assign a value to the chosen variable. So we can say that once a variable is selected, you then pick a value for the domain, right? To assign to it again. So there can be heuristic here has like least constructing value to for choosing the neighbors variables. So here we have consistency check. Check if for current assignment is consistent with the constructs, right? So after the making an assignment is it's crucial to the check if the partial assignment of volatiles of any of the problems constraint. This checks vital for the efficiency of backtracking. If the current assignment newly assigned or satisfied all or not, or retrieved constraints, you can proceed. If the violate of any constraint, this path is immediately considered as a dead end like that. So recursion, if the assignment is consistent, recursively they try to assign values to the remaining variables, right? So if the assignment is consistent, recursively try to assign the value to the remaining variables. If the current assignment is a consistent, then algorithm makes a recursive call. This means it efficiently repeats the step 2 5 for the next unassigned variables, like building upon the current partial solution. This continues until either, right? Here we have backtrack. If the assignment is not consistent or if further assignment do not lead to the solutions, undo the last assignment backtracking and try the next possible values. So usually here we can say that if the assignment is not consistent, the consistency checks and fails the current assignment or recursive call for next step to return indicating that no solution could be found by extending this current partial assignment, right? So here we have the example of CSP NQ. We have a problem placing NQ on an into n chessboard so that no two queens treated each other, right? So we have a Q NQ problem. So we have first discussed in theoretical way. In next lecture we discuss in it code. Okay. So here we can say that NQ problem of CSP has problem definition. The NQ problems ask us to place n, right? So ask us to place n, right? So here we can say that chess queen on the n into n chessboard such that no two queens threaten each other. A queen can attack here horizontally, vertically, and diagonally, right? So we do not place any two queens in each vertical and horizontal. So implementing backtracking such algorithm to solve the CSP. Here the Python implementation of backtracking such algorithm to solving simple CSP. So first we discuss it the theoretical way. Then after we move into the coding. So the NQ, here we have the output like this. So we can see here, no in row or column we didn't mention any each of the queen, right? We mentioned each row, each column, but different places we mentioned the queens, right? So no one is there in particular way. So here the process of taking this. So we have some values like we want to assign in mapping like variables. We have the domain, we have to constraint on it, and then implementation of backtracking on NQ like initialization, step selections, assignment, construction, checking like we are discussing previously, recursions, and backtrack. Like that, we use all those methods. So here comes to the roles of backtracking of solving CSP. So we have some roles of backtracking in CSP. So first one is applications of backtracking. So applications of backtracking here we have optimization and technical problem. So while pure backtracking primarily um, finds a solution to the CSP, right? It forms a basic from the more advanced algorithm that tackle optimization problems. For example, in a branch or bound algorithm which are used for optimizations, backtracking helps to explore the such space, like while bounding or branches that cannot be lead to the better solutions, like dynamically environment we have. So constraint satisfaction problem CSP. So this is the one of the most directed and fundamental application has discussed problem like n queen Sudoku map coloring and puzzles and solving. So it problems are classic CSP solved efficiently with the backtracking of the enhanced with heuristic and the constant propagations. So electrical engineer. So backtracking can be used in circuit designs and verifications. For example, in the designing integrated circuits, ICs and placing them components on chips or routing connecting of the often involves satisfying numerous partial and electrical constraints. Right? Backtracking can explore different layouts to find a one to meet another specific right. So robotics, backtracking can be applied to the path planning problems, especially in complex environment with obstacle. A robot need to find a sequence of movements for a start to the goal and position, right? Start to goal position and while avoiding the collisions and respectively kinetic constraints. So backtracking can explore the different movements and different sequence, and we use mostly in artificial intelligence. We have know that. So in artificial intelligence, there is a like good bond category has backtracking is a core search technique with AI. Beyond CSP is a fundamental foundational too. But when we use gaming AI, automated planning and logical programming, we use theoretical and theorem proving, exploring the different proof path in logical say, statements like logical systems in we use a genetic and bioinformatic algorithm, right? So bioinformatic. So in while generating algorithm or evolutionary, some of special problems within the bioinformatic can leverage the backtracking. For instance, in sequence alignment or a protein folding, exploring the like we can say space or elegance sequence under the constant might involve a subprogram for that benefit for a systematic and depth first exploring, right? We have a good for phylogenetic tree construct, and some methods might be used in execute the search backtracking in optimal tree search structures. So material engineering, we also the similar to the electrical engineer, material science and engineering might use the backtracking for the problem involving the material designs and optimization for material properties that could involve the searching for optimal compositions or microstructures that satisfies a set of desired properties and constants. Network communication. Backtracking can be applied to the network routing problem where you need to find a path through a network that satisfies the certain criteria. Like solving puzzle, we all know that we used to solve these puzzles, especially applicable on Maze, Sudoku, and Rubik's Cube, and like that. So in this, we have the advantages of backtracking. So we have a simplicity. The algorithm is too easy to implement and understand, right? So the algorithm is most easy and to implement to understand, but and it core to receive nature. Backtracking makes the like understand and basic implementation quite straightforward. It mimics a systematic trial and error approaches, right? So efficiency, it works for well and for many partial CSP, especially when combined with heuristic. So we can say that. While often described as a brute force approaches, if effectiveness comes from the crucial pruning machines, when a partial assignment volatiles the constant backtracking immediately cuts off the entire branches of the such tree. So we can see that for flexibility can the adopted of the optimized with the various strategies like variables ordering and constant propagations. So here we can say that we have some if, flexibility like this is a major strength of backtracking. Is not a rigid algorithm, rather it provides a robust framework that can be signified enhanced. Right? So in this we have variable ordering and value ordering and construct propagations we use to check in our consistence. So like that we use in it. So we have the disadvantages. Backtracking approaches is not efficiency for solving strategy problems, and the overall runtime of the backtracking algorithm is normally slow. To solve large problems, sometimes it requires help from other techniques like branch and bound, etc., and requires a large amount of problem memory space to store the different stages, functions, and stack too for a big problem. And hashing is one of the main issue in backtracking. And the basic approach is to detect conflict to the late. So here we have the optimization techniques too. So we have the forward checking. We have the forward checking like how after assigning a value to a variable, eliminate the inconsistent value from the domain, right, of the unassigned variable. So how it works when you assign a variable to xi, forward checking immediately, looking at the unsigned variable xj. So that are were connected to xi by a constant, right? For each such xj is removed, so it benefit is to this is the formal protective plugging instead of waiting to discover an inconsistent only when xj is selected and a value is assigned to it. Forward checking, identify and removing the impossible values early cannot lead to a solution, and the algorithm can immediately backtrack. So this significantly reduces search time space. So construct propagation. Use algorithm like AC3 or consistent 3 to reduce the search space by enforcing constants locally. So how it works like a constant propagation is a more general and powerful from the domain reduction, right? So then forward checking is ensured that for each constant that value in the domain of each involved variables and consistent with the other, right? So R consistency is a variable xi or consistent with respect to another variable xj. If every value in xi is domain and there existed at least one constant value in xj. If not, inconsistent value are removed. So this is a widely used algorithm to enforce that consistent across the entire CSP. It works by the maintaining the queue of the arc that need to be checked when a value is removed from the variable domain, all the arc pointing to the variable. So until no more, the process continues until no more domains reductions can be made or an empty domain is discovered. So we have heuristic. We can say that it is how it works like when we deciding which unassigned variable to choose next, select one of the which fewest legal values to remaining in domain. Like heuristic are not about the value from the domain, but also an intelligent ordering of choosing it during the search, right? So they guide the search towards a more promising path. So we have the limitations too. So in limitations we have the uh, inefficiency for large problems. So the algorithm can be slow for the large or high consistent problems. It may be this is the most significant limitation while backtracking in a semantic search. So and pruning the mechanism helps that to fundamental problems remain the explosion. For the example, with a very large number of and large domain size and weak constructions, even optimization like that. So we have redundancy. So without optimization technique, the search might be redundancy, explore many invalid paths. So this point is highlighted while optimization like constant propagation, like also crucial. So in basic backtracking implementation, an inconsistent might be only be detected when a variable is finally chosen and assigned a value. Before that, many fault assignments it might have been made to previous variable that ultimately lead to the each space complexity. So it requires a significant memory for the storing the state of the such tree, right? So backtracking is inherently a depth first such like a recursive implementation in called the stack implement like implicity storage to store the path for the root of the such tree and the current node is the means it store the assignment made to all variables like up to the current depends, right? So for the problems with a large value the depth of the recursion can be substantially lead to deep calling stack. Each stack frame consume memory. So we have the final conclusion here. So backtracking search is a fundamentation technique for solving the constraint satisfaction problems by systematically exploring possible variables, assignments, and backtracking when constraints are violated. It can find solution efficiently for many practical problems. However, its performance can be significantly enhanced through optimization technique use like forward checking and constant propagation, understanding backtracking search, and it applications is crucial for tackling a wide range of the problem in artificial intelligence and computer science. So overall, this is the solvation constant. We use the most of the technique use and roles to come in the backtrack solutions to in efficient way. So we use most in CSP because in the puzzle solving or a graph tree we use in most of the decision multiple decision times we can choose the easiest path to take the backtrack. It mostly uses in a large scale, but when we use to backtrack, we use set of roles and techniques we use in backtracking that may help us to backtrack easily to return the parent node by using some kind of technique use. So it is a wild range. It is tackling a wild range of problems in artificial intelligence. So it is used for solving the wild range problems in computers in intelligence, artificial intelligence. So I hope you guys all are understand about the backtracking. So in next lecture, we will discuss about that NQ problem. Okay. So until that, thank you all of you.